Okay, hi. Yeah, I think my Zoom crashed. I'm just waiting for questions.
Okay, yeah, I'm having a little bit of trouble with the Dijkstra's algorithm and hash tables and some of the very later stuff we did. So I understand exactly what's going on. I understand the algorithm, all that. But I'm having a little bit of trouble with the actual implementation, and I'm scared that if it comes up on the exam, I might have to work it out a little bit harder than I would otherwise have to. So I was wondering if you could go over a couple implementations of those.
A couple of implementations.
Oh, maybe just one of each, like not several of each.
Uh, okay. So yeah, so I think that's also linked in the slides. It's just like easier to do Control F here.
Yep.
Uh oh, that's the one that we haven't actually done. Never mind. Yeah, all right. So let's maybe do like a Python hash table. So basically, what we need to do is we need to create a linked list. This. So basically what we need here. So let's do a node. So node. Yeah. Okay. So something like this. Does this make sense? So this is just like a standard linked list, right?
Yep.
So then so now we're doing like a hash table thing. So a hash table is basically a list with a bunch of so a pre-made list with a bunch of linked lists, right? So this would be okay. So we have our slots, and we'll do so. The size is, let's say, whatever, 1,000. So we'll make a hash function. So if it's integers, then that's all we need, right? So just like mod. And then put would be basically, so we'll import linked list. So put would be figuring out the location. So the location is just the hash. And then at that location, if it's none, then we'll put a linked list there. If it's not none, then we'll put the key. So we're just doing the key. So if there is already stuff there, then we'll just add the key, right? So if location is none, then we'll do this and we'll add the key. So like either way, like either we create an empty linked list and put it in slots location, or if it's not none, then we just add the key. And then here, the location would be again the hash. And then if the slot that corresponds to that location is none, then that means it's not there. If what we have there is a linked list, then we need to check whether that element is in the linked list. That is it.
I see. Could you just explain the last one again, please? The is element. That's okay.
Yeah. So we have the slots. Some of the slots are none. Some of the slots are linked lists. So we say, okay, so if the key is in the hash table at all, it's at slot location, right?
Yes.
So if it turns out that slot's location is none, then that means the key is not there. We just return false. If slot's location turns out to be non-empty, so it's a linked list, possibly with one element, possibly with multiple elements, then we just ask, is key an element in that linked list?
Okay, I see. Okay, wonderful. Thank you.
Mhm.
Could we also do an example of Dijkstra's, please?
So again, we need to like define. So so find node again. So here it's not like a linked list node. So this would be like neighbors, right? A set. And then a graph is just so let's say that it's fully connected. So so whatever. So the graph is going to look something like this, right? So that's what we've done before.
Yep.
So now with Dijkstra, so we have start. So visited is initially empty. And then we'll have, well, we can do it like that. So I guess I'll do kind of like the elementary one without the priority queue. So what we need to do is we need to keep the distances. And that's going to be this. So the distance from the current one is just 0. Oh yeah, that's a good point. So okay. And then this would be item 0 now. So now we'll say basically okay, we'll break later. Yeah, that makes sense. So we'll say, okay, so we'll look for the smaller, so again, the picture would be we'll look for a V such that S to U plus UV is as small as possible. Right? So what we say is, okay, like what? No. Oh yeah, so this is for every key in Kurdis, which is the same as for node and for node and visited, right? And actually, this wouldn't work. Yeah. So and now we're sorry. So this would not actually work because node is okay. Well, we'll do it like that. Okay. So here we're saying, okay, so if node is not been visited, no, that makes no sense. So what we'll say is, okay, so like for every node and visited, so we also need, so I'm doing it kind of like in the simplest way possible, which is going to be a little bit awkward. So a set needs to, so we need the kind of those guys, but we can only find them using a dictionary as well. So I'll just check. Okay, so now I am able to access all the airports by using like str to know the YYZ or whatever. Does that make sense? So, okay, so now I have the visited and I have my current lists, which is going to be str to know that start like this. And now I'm saying for node and visited. And then for neighbor. So for every neighbor of a visited node, I'm saying if the neighbor is already visited, then skip.
What's the syntax of the for loop again for neighbor, comma, dist to neighbor? How does that work again?
So current distances is the names of the nodes and the distances to them. So I'm putting the name of the neighbor and the distance to the neighbor in neighbor dist to neighbor.
Sorry, could you explain that again, please?
So cur dists looks like this. Something like that.
Yep.
And then putting like YYZ the neighbor, 0 and dist to neighbor, and so on.
Oh, okay, I see. Okay, great. Thank you.
Okay. So I want to do it like this. So this would be you, and this would be this to you.
So like is current this basically the current node or the current airport?
No, so this is like the distances that we've already recorded.
Okay.
All right. So now we're saying, okay, all right. So we have the U that's already visited and the distance. And now I want every neighbor of U. So for V in the neighbors of U, right? And now if V is in current distances, then it's been already visited. So we just continue. Otherwise, so that's the same. So we don't really need visited. So we're just using current distances. So otherwise, we'll say, okay, so here, like current dist is going to be like a very large number. And then we're going to say if distance to U plus the distance between U and V. So here I actually said like for V, so I should have said for V, comma, dist, right? So I'm getting like V is whatever this, and then this is this. Right? You want to do it like so. Yeah, sorry, I'm like trying to make it simple, but because it's not prepared. So we're saying, okay, so for V in this, so if V is in current distances, then no. And then if this to U plus the distance between plus distance is smaller than current dist, then we update current dist. And here, if we haven't found anything, then that means that we're done. Otherwise, there would be a non-infinity distance. So at this point, we just add Curtis Kerman node to Kerman dist. That's it. That is definitely not how you say Dijkstra. All right. So the basic idea, so here, like I tried to make it as simple as possible. So the basic idea is we keep the distances that we already recorded. So in this example, you have the distance from S to X and you have the distance from S to U, right? And then you're saying just like for every node in the visited set, so for X and U in this case, try all the neighbors of X, try all the neighbors of U, and see what this and see which distance is from S to X to Y as small as possible, is from S to U to V as small as possible. Find the smallest one and record the minimum distance. In this case, if S to U plus UV is as small as possible, then record S to V as being S to U plus UV.
Okay, yep, that makes sense. Thank you so much.
Yeah, like you can just speak up if you want to ask something. Will be asked to implement Dijkstra on the exam? I know. Yeah, sorry. So like people keep asking me, and like the only reasonable policy is to just never say no, because like the point of the exam is to make people study as hard as possible. So like if I start saying no, like first, like people are never going to stop asking until they like exhaust all the possible questions except the ones on the exam, I suppose. So yeah. Like it definitely would not be an easy question if it were asked. What is the difference if you, well, I mean, like if you need to implement it in C, it would be quite annoying to do, especially if it's a graph representation. So if you're doing it with a matrix representation for a graph, I guess it's not so bad.
Wait, so for matrix representation, are we talking about like adjacency matrix?
Yeah. Because like here, like even in Python, you see that it was kind of awkward to do, right?
How do I keep track of the edge distance if it's an adjacency matrix?
I mean, just in the matrix, you just, instead of ones and zeros, you put in the distances. Very
Or
convenient.
would you have like tuples inside the matrices?
No, you just like, so and then
Oh, I see what you mean.
you put in the distances. Yeah, so like YZ to YUL is like whatever 500.
Oh, okay. And then I guess you put like infinity if they're not connected,
Yeah,
or
for
like
example, yeah.
-1 if they're not connected, right?
I mean, you could, so infinity is like more convenient, I suppose. Yeah.
Does that exist in C though? Infinity.
For floats, yeah.
Okay.
To use Infinity, I think we have to import something, right? Some of the questions on the exam say don't import any external libraries. So what would we do if the question said that and we had to use Infinity?
That would be a weird situation. I mean, I suppose you could always like use a really large number or something.
Okay, and that's reasonable to do?
I would say so. Oh, so like I would say it's reasonable to do unless the question specifically says that you're not supposed to.
Okay, sure. Great. Thank you.
And then like, it's like you could always kind of like instead of storing it, so like just hypothetically, right? So you could always say, I'll make my own. Right, so something like this. So you like this is not super efficient because you're storing an int every time, but it would do the job, right? Why for linked list complexity of insert? So yeah, so we discussed it in lecture a little bit, right? So if you know the location where you're deleting or inserting, if you're keeping track of where it is that you're supposed to insert and delete, then inserting and deleting is just a matter of like rearranging two connections, right? So if you don't, like if you just want to insert at location I and you don't have the pointer to the I minus first node, then it's all then. The reason this comes up is that when you're implementing a stack or a queue using a linked list, there is no problem in terms of inserting or deleting because you only ever want to insert or delete at the ends. And if you only ever want to do it at the ends, then there is no issue with just saying, well, I'll just, I'll store a pointer to the first element and I'll store a pointer to the last element. And then if I want to insert or delete at the end or in the beginning, then this is really all one because I just need to rearrange a couple of edges. Does that make sense? So it's not the same for get. So it's like this is a matter of definition. So if you are already storing the location of the node from which you want to get the value, then sure, it would be all of one as well. But if you're already storing the location, you could just also store the value. So like the get operation wouldn't really make sense. So like the get operation only really makes sense in the context where you don't know where the node is. Because if you know where the node is, you could as well just know what the value is as well. So in particular, like if you only ever want to get the element at the end or the beginning, that would be all of one because you could just store them as you go in the same way that we would store the location of the beginning at the end. With that said, you're right there that there is a non-uniformity there in a sense that, yeah, like if you treat those like exactly the same, then yeah, like they would be either both of one or both of n. It's just that for inserting and deleting, it makes sense to say sometimes, well, you happen to know the location. For get, it never makes sense to say, well, like, what's the complexity of get when you know the location? If you know the location, you also know the value anyways. All right, I think that's the end of it. I will see you tomorrow if there's no more questions. No? All right, I will see you. Bye. Good luck.